Okay, so today's lecture is day 2 in physics. So this is for Monday, May 18th. Before I forget, I want to let you know that I will have an assignment for you that goes with this lecture, but I probably won't get it uploaded till, because I'm tweaking it, kind of revising it from the last time I taught. It'll be done by tomorrow, Monday. Today is being Sunday, but I'll have it done for you by the end of the day on Monday. So I just want to say that at the beginning here. So we're going to be talking about the concepts of mass, weight, density, and pressure, and trying my best to relate to them on how they apply to what we do as respiratory. Alright, so again, just a lot of terminology here. Mass sometimes get kind of confused with weight, or it's kind of interchangeable in a way, but not totally. You'll see what I mean. But you'll see how they talk about mass and weight a little bit interchangeably in our one of our equations coming up. So mass basically is the measure of the number of atoms in an object combined with the density of those atoms. Okay, so mass and weight definitely aren't the same, but some of the equations, they kind of use the term a little interchangeably. All right, so mass then basically measures the quantity of the matter regardless of both its location and the gravitational force applied to it. So the typical units for measuring mass are either kilograms or grams, which is really how we measure also weight. So we look at it as the measurement of the amount of substance in a body. So what you're made up of, okay? So it's how much kind of area you take up, space that you take up. So your mass on Earth and on the moon are identical, so you take up the same amount of space. However, your weight, which has to do with the gravitational pull, your weight on the moon is about 1/6 of the weight on Earth. Okay, so it's kind of like the amount of substance. Okay. All right. So then weight then is really the force of an object that results in from that gravitational pull. Okay. So density, and this is where I'm talking how sometimes it gets a little confusing. Density then is the ratio of mass divided by volume. Okay, but sometimes you'll see that mass is the weight. Okay, and we'll kind of look at that a little bit more later. But so density then, so if you want to write it out, it's going to be on the next page. But density, D equals M for mass, divided by volume. Okay, so this is kind of where sometimes it gets kind of flippy-floppy, I guess, with the terminology. So when you look at something dense, okay, it's going to have a heavy or a high atomic weight. Okay, and that's something that we can determine, look at the periodic table of elements to help us determine atomic weight. So the particles then are closely packed together. Okay, uranium is very dense. Okay, so it's a real dense subject, so it has a high atomic weight. Or hydrogen is a good example of a low density substance. Okay. And so it's lighter. It has light atomic particles per unit of volume. So when we look at the periodic table of elements, so hydrogen then has an atomic weight of 1, okay, or 1.008, compared to uranium, which, let me see if I can find uranium quickly. And uranium has an atomic weight of 238. Okay, so just kind of comparing those two things. So uranium being more dense and hydrogen being less dense. Alright, so here's that little equation I was referring to, how your density equals mass. So this is the equation I was talking about, the calculation. Sorry, my dog started barking again. So we have density equals mass divided by volume. Okay, so in clinical practice, this is where I was talking about how come sometimes it gets kind of substituted, that weight is often substituted for mass. And then so then it's referred to as weight density. So a D with a little W is what's actually measured. And you can refer to page 114 in Egan. Egan does a good job of talking about density. So that would be your best resource to follow along with this lecture. And then our solid or liquid weight density is then measured in the grams or grams per cc. So grams per cubic centimeter is a cc. And then for gases, the most common unit then is grams per liter. Okay. Don't worry too much about that. I mean, when we start doing any type of calculations, just follow the units that we're working with, and then you should be okay. So you will be doing a few calculations with this. So because weight density equals, again, mass, or weight divided by volume, the density of any gas at STPD, and I'll talk about that in a second, can be computed by dividing its molecular weight, so GMW is gram molecular weight, by the universal molar volume of 22.4 liters. Okay, so STPD is standard temperature, pressure, dry. Okay, so it doesn't take an account of humidity or water vapor. Okay, so STPD is standard temperature, pressure, dry. All right, I know this is kind of another Greek language here, but hopefully it'll make a little more sense here as we go along. So the main things you're going to have to do is do some calculations with density on this, and then in the next few slides we'll be talking about pressures and flow, which I think are a little bit more relatable. So when we look at, again, STPD, so that's standard temperature, which then is 0 degrees Celsius, and pressure, 760 millimeters of pressure is like your barometric pressure. That would be like your standard barometric pressure. That's like sea level, 760. So our barometric pressure here in Denver is lower because we're up at higher elevation. And dry, then, so you're not using any water vapor pressure. So then the ideal molar volume of that gas, of any gas, is 22.4 liters. So we look at density equals gram molecular weight divided by 22.4 equals the density in grams per liter. Okay, so just recognize that number of 22.4 grams per liter is the ideal molar volume of any gas. Okay, so 1 gram molecular weight equals, again, 1 mole of gas at standard pressure, which equals 22.4. So that's just like a constant, basically. So when we're looking at BTS, I'm just kind of throwing that in there just as a different thing that you might see. B as body temperature, pressure standard, okay, body temperature. That actually takes into account water vapor. So when we do certain calculations, like when we do the alveolar air equation, you'll see that we actually subtract 47 away. So 47 millimeters of mercury is a water vapor pressure at 37 degrees Celsius, which is actually 98.6 Fahrenheit. So 47 millimeters of water vapor, we would always subtract then from whatever the barometric pressure is to do our calculations for our alveolar air equation. And you'll see that demonstrated here probably in the next lecture or two. We're given a barometric pressure, and then we always have to subtract 47. Again, 47 just being a constant. Okay. So remembering that's the water vapor pressure, again at body temperature, normal body temperature, which is considered to be 37 or 98.6, depending which unit you're using. You're using temperature, but what type of measurement? All right, I know it's a lot to talk about, especially when over doing this online or recording. So Avogadro's law, I just want you to kind of be aware of it. I want you to be able to recognize it and be able to name it. I'm not going to ask you to use that constant to calculate anything. Okay, so don't freak out when you see this. Maybe you've heard of it before when you're doing chemistry. But a major principle then in governing chemistry is Avogadro's law. So basically what it says is that 1 gram of atomic weight of any substance contains exactly the same number of atoms, molecules, or ions. Okay, so this number, the 6.023 times 10 to the 23rd, is Avogadro's constant. So it's a standard international unit. Okay, so this quantity of matter equals 1 mole. Okay, so that number equals a 6.023 times 10 to the 23rd is equal to 1 mole. So that's Avogadro's constant. So the law states that equal volumes of gases under the same condition must contain the same number of molecules. At constant temperature and pressure, 1 mole of gas should occupy the same volume as 1 mole of any other gas, and this is termed molar volume. Okay, so this ideal volume is termed molar volume. So again, we have a lot of terminology here. All right, so talking about air, density of air, you should know that the air that we breathe is approximately 21% oxygen and 79% nitrogen. Okay, and a really small part of inert gases. That's why I wrote approximately 21%. It's really 20.9, but we usually just say 21% is considered room air. So a lot of times you'll just hear it referred to as room air. We don't say that they're on 21%. We'll just say that they're down to room air. RA is definitely abbreviation for that, or 0.21. So I know that was kind of a question way back at the beginning on your periodic table. I think it was like the last question. It was what makes up most of our air or something. It's actually nitrogen. So, all right. Okay, so now it gets a little bit hairy here with some of the math part of it. So again, this is out of Egan's page 114. So if we're looking at trying to calculate then the density of air, we need to know what the percentage of each gas mixture is. Okay, so if we're just looking at regular room air, okay, that we're breathing right now, so again, to calculate the density of air at STPD, so at standard temperature, pressure, dry. So the F means your fraction. Okay, so you have your F up here in for the density of gas mixture to be calculated, the percentage or fraction. So it's a fractional inspiration of whatever your FiO2. So your fractional inspiration of a gas. So when they say what FiO2 were they on, F, it's usually a big F, a little I, and then O2. How much percentage of oxygen? Because we can adjust that. We can actually go up to 100% oxygen if need be. Okay, so we need to know how much, in this case, how much of each gas mixture. And so we're just talking about room air here. So the F then is your fraction of oxygen, or your percentage of oxygen. So if we're looking at this calculation, so we have density weight, okay, of air. So FN2, and if you look right below it, then we have 0.79, because we just said on the previous slide that the air that we breathe is about 79%. Okay, so when we're working with this type of calculation, we're going to use it as a decimal. Okay, so we're going to convert again. This is why we're working on this kind of stuff on math, is learning how to switch from percentages to decimals. So 79% is the same as 0.79. Okay, and then the 28 actually comes from the periodic table of elements. So if you look at nitrogen on your periodic table of elements, and the nitrogen is N2, it's not just N by itself. N2, the atomic weight or mass of nitrogen is 14. Okay, so we do N2, so we do 14 plus 14 equals your 28. Okay, so that's that part of the equation. So this is kind of where all this crazy math that we're doing with, you know, percentages and decimals and PEMDA of which order of operations, that's why it's important. Okay, so we put that in parentheses. Okay, so that's part of our equation. Then we're going to add, we're going to do the same thing for the fraction of inspiration of oxygen. Okay, so we have 21% is what we're breathing, so 0.21, and then oxygen's molecular or atomic weight or mass again is 16. Okay, so it's weight, or yeah, it's weight or it's mass, 16. So we have 16 times 2 then is 32, right? So what we're going to do is you're going to actually take each part of that equation. Okay, so you're going to take the 0.79 times 28, figure that out. Then you're going to take the 0.21 times 32, and then you're going to figure that out. And then you're going to add it together, and then divide it all by that constant of 22.4 to get it to grams per liter. Okay, because your other units will cancel each other out. So you've got grams per liter. So the density of air then is 1.29 grams per liter. Okay, and that then being a constant too, because that's just going to stay that way. I mean, if you're talking about regular room air without any supplemental oxygen, that's how much the density of air is then, is 1.29 grams per liter. Okay, using that mole calculation of the 22.4, which was a couple slides back. Yeah, the universal mole being 22.4. I know, it's like, what are you talking about? But that's how you figure out density. Okay, and we'll talk about why it's applicable here. So hang on for the ride here. All right. So gases then share many properties with liquids. So gases exert pressure, they can flow, and they have a property of viscosity. Okay. Hold on. All right, so all these gases share different properties. They have gases exert pressure, they flow, and they exhibit the property of viscosity, which we'll talk about coming up. Contrasting to liquids, gases can be compressed easier and expanded and fill spaces that are available to them through diffusion too. All right, so when we think about gases, you think about gases in a container, and the more gas molecules colliding with the wall exert small forces on the wall. So basically, the more gas, the more molecules you have, the greater the pressure. So the pressure basically then is the sum of all the different collisions. Okay, and we can speed that up by heating it. Okay, that's one of the things that you can, change is by heating a gas, and the particles are obviously going to move around faster. They're going to take up more space, and they're going to increased pressure. And we'll talk about that more when we start talking about different gas laws here. Not today, but coming up. Alright, so we are going to be talking about flow. Okay, so patterns of flow. And this has to do with the pressure gradients. And for right now, we're kind of referring a little bit to fluids in this, but it also will apply to gas too. So we have a pressure gradient. So you have to understand the pressure gradient, that is the difference between the pressure at the beginning and at the end. Okay, so we'll be talking about Poiseuille's, I can't say it in a fancy way, Poiseuille's law. Okay, and we'll talk about, like, the greater the pressure gradient, the greater the flow. Okay, so the greater you have from the beginning of P1 to P2, the greater that number is, the greater the flow. Okay, so the gradient of the fluid then is the difference between the starting and the finishing pressures in a confined tube, which then is actually, if we do all the calculations there of looking at the change of pressure divided by flow, or the change of flow, then we have that has to do with resistance. And we will talk a lot about airway resistance as you get in more into the physiology of respiratory. So when we look at P1, we can kind of look at that as our pressure upstream, and P2 as our pressure downstream. Okay, so we have two different pressures going on. And then flow, you'll see flow sometimes being represented as a V with a little dot kind of in the middle of the V, kind of towards the top. That is flow, and flow is liters per second. So one of our common units that we use in pulmonary physiology is centimeters per liter per second. Okay, centimeters of water pressure per liters per second. So that's actually a unit that we use when we're talking about resistance. So this is just kind of, I don't expect you guys, I know it's a lot to kind of get in your head, especially when we can't really talk about it and answer questions. But again, it's kind of like sprinkling this information because you're going to be hearing it over and over and over. So you think about flow and how it wants to equalize. Okay, so it wants to distribute itself evenly. So we have at the beginning on the left side, you have a pressure, your P1 is 20 and your P2 then being 5. Okay, so you have this difference because it wants to go downstream. It wants to take the path of least resistance. So your gas flow there is being demonstrated with the driving pressure then of 15. So it's just basically the difference between P1, which is your 20, and your P2 being 5. So 20 minus 5 equals your 15. So that's how much driving pressure. So Poiseuille's, there's a nice little video that you have a link on this lecture too that talks about, it's about maybe 8 minutes long. And it kind of shows how if you have a longer tube, then you're going to have more or a bigger pressure difference or pressure gradient, which is going to increase your flow even more. Okay, and how I'll talk about something in just a minute here. I get excited, but I need to just slow down and think about what I'm saying. Alright, so this is a diagram out of Egan. This is page 121. And it's kind of showing how on the left side there, the pressure is the same, okay, because there's no flow. There's nothing going on. If you look at the bottom right on A, there's like a little plug there, okay, so there's no, it's not open, so you can't get any kind of flow, okay, going on here. So the pressure is the same at along all points, no matter the size of the tube here, okay, because there's no flow going on. And then on the right side, on B, then they've opened up the little cork or the plug there, and you can see a progressive decrease in the pressure as the fluid flows. So when the fluid flows out through the bottom of the tube, the pressure progressively decreases along the tube length. this decrease in pressure between each of the evenly spaced vertical tubes is the same. So it's kind of proportional to how spaced out the tubes are. So that's on Egan's. You can refer to that for more info. So before on the left side, the other thing I wanted to say, when there's no flow, just kind of remember this term is static. Static, S-T-A-T-I-C, static, no flow, nothing going on, okay? So static, you're just kind of chilling out. And we'll talk about that more too, because we talk about airway pressures, of changing airway pressures and static pressures. All right, so different types of flow, okay? So we have laminar, turbulent, and transitional flow, okay? So a laminar flow, I think of always like a smooth flow. Laminar is just nice and it's found in a smooth tube. The fluid moves in discrete, cylindrical, or streamlines. We like nice smooth laminar flow. Okay, so Pizzelle researched this and determined that the laminar flow rate of a fluid along a pipe is proportional. Well, you'll see the equation coming up on the next page, is proportional to the fourth power of the pipe's radius applied to pi. So remember pi, that little squiggly sign, and you'll see it on the next page. He also said that the flow rate is dependent upon the fluid, which is represented, the fluid viscosity, which is represented by this little funny N. I forget the name of it, but it's got some term. And the pipe length, which is L, and then your pressure difference, your pressure gradient, okay, your P1 and your P2. If you click on this link, he does a really nice job of explaining it all. I'm going to talk about it a little bit more on the next slide too. All right, so this is what I'm talking about. So this relates resistance to gas flow depending on the radius and the length of the tube. Okay, so your flow then equals to your change in pressure. So your P1, P2, that change in pressure. So for example, if you're looking for like a number or whatever to put in there, if we looked at that problem with the beginning pressure of 20 and the end pressure of 5, then the change would be 15. Okay, so remembering, I don't know, maybe you don't know this, but the triangle sign is delta or change. Okay, and then your radius is actually, and he explains that your radius then, depending on the diameter of the tube, or the radius of the tube, is actually to the fourth power. Okay, and he explains that well. If you're looking at a tube and then you double the radius, it actually goes up to so a change in the airway diameter by 2 actually increases it by a 16-fold. So it goes up, you know, to the fourth power in airway resistance. And then 8 being a constant, you have L being the length of the tube, and then you have N as the viscosity. Okay, so a change then in the airway diameter by 2 can cause an increase of 16-fold change in airway resistance. So why this is important to us is if we think of a smaller tube, okay, so we think of a smaller tube, we can think about this as a smaller ET tube, a smaller breathing tube that we might put in patients. Sometimes they'll insert a little bit smaller breathing tube into somebody if they're a difficult intubation and they just for some reason can't get a bigger tube in because they have airway swelling or whatever else is going on. So that's going to increase their work of breathing, as is airway swelling in general. Because you think about that, your airway is tightened, like in asthma or any type of inflammation or secretions or whatever, that is going to increase your airway resistance, and that's going to increase your work of breathing. Okay, so that's why this all kind of comes into play. Kind of seems like a long way around it, but just so you're understanding kind of the basis of it. Okay. So if you look at this, thinking that if you increase the tube's radius by 19% even, this will actually increase the flow by 100%. So resistance, area resistance, is very sensitive to changes in tube radius. So as you increase the radius of something, you're decreasing the resistance. Okay. So if you're making something bigger around, for example, when we give medications, bronchodilators, to help open up the airways, we're increasing the diameter of the airways with that medication. So we're helping bring down airway resistance. We're making it easier for them to breathe. Okay. Increasing the length of the tube, which really, other than the breathing tube, which I mean they're pretty standard. Sometimes they'll cut them off, mainly so in kiddos, just because the diameter of them, the little ET tubes that they use to intubate babies, are so tiny around, like little stir straws. Sometimes they could kink off easily, so from the weight of the circuit, so that's why they sometimes snip those off. But just thinking as another thing of increasing length is going to increase your resistance also. But mainly increasing your radius is going to decrease your resistance. And plus that little lecture does a nice little job of explaining it with the diagrams and stuff, pictures. Alright, so we would like things to be laminar in our flow if we can. Okay, we don't want things to be turbulent, because when we talk about turbulence, we're talking about molecules that are bumping all over the place. They're irregular currents, they're in a chaotic pattern, and things are going to be more turbulent if they have more resistance. Okay, so it's can be dependent on your density, on the viscosity. So I'll talk about that in just a second. I'm kind of holding on to some of my thoughts here. Linear velocity, again, your tube radius. So if you have a narrower tube, you're going to have increased turbulence. Okay, so you have increased pressure, increased turbulence. And these factors kind of give us a number called the Reynolds number. And to be quite honest, I don't really remember learning about the Reynolds number. Maybe I did. One of those things that I forgot that I learned. But it could come up as it will come up as a test question, just so you understand which number is normal, considered a good number. And it may be like a speedable when we do the little trivia stuff. So your Reynolds number is determined by your density times your velocity times your diameter divided by viscosity. Okay, so just keep it the number. Oops, I think I have a typo here. I do. How funny. I'll have to change it. It's 2,000. Okay, so we would like to have I have greater, hold on one second. Alright, I just wanted to clear something up. I had one thing typed on my notes here and then something different on the PowerPoint. So a Reynolds number is also covered in Egan's on page 122 in your textbook. So if you have a Reynolds number, again, it's just kind of like a reference number. If it's greater than 3,000, then your flow is considered turbulent. Okay, and then if it's less than 2,000, then it's considered laminar. So there's an in-between number, which is transitional or transient. Okay, so that's kind of in between, which makes the word transient. So about 2,000 to 3,000 is kind of where we're normally at. Okay, so we would like to have things as laminar as possible, but our natural physiology of our body, we have a combination. We have more of a transitional flow is really what's going on in the respiratory tract. So you think about some of your bigger airways, your trachea, and that is probably more turbulent because it's just has a bigger diameter. but as you get further down, you're hoping that things are more smooth and more laminar. Okay. So again, the transitional flow is in between the 2000 and 3000, and our whole tracheal bronchial tree is an example of being a mixture. And just a little bit of a visual here on laminar flow and turbulent flow. Okay, so one of the different examples that I wanted to talk about was a couple different ones. So you've probably all have seen people use those inhalers, okay, those little meter dose inhalers. Maybe some of you take them, or a family member or somebody. The reason they like to use the spacers, those little aero chambers in between the inhaler and the mouth, is that the reason being is that if you shake your little inhaler, you squeeze it, you suck in, a lot of it hits the back of the throat and it's turbulent. Okay, a lot of the particles just kind of bounce around, they hit the back of the throat, they really don't deposit as deep into the lungs. So if you actually squeeze it into that aero chamber, or that little chamber, it gives the particles a size to get a little bit smaller, and then as you take a slow deep breath, you're not supposed to make it whistle, you're not supposed to take a fast deep breath and make them whistle. People think they're supposed to whistle. They're not supposed to whistle. So a nice smooth slow deep breath, you're creating a more laminar flow. So hopefully the deposition, the idea is that the deposition of the medication gets down into the lower airways, where that's where you want it. You don't want it all in the back of your throat or in your trachea, because that's not really that's not the tissue that you want to affect. Okay, you want it further down into the lungs. So that's one of the ways how I explain the reason that we use inhalers. Maybe not quite that much in depth, but for our patients, but it just creates a more laminar flow. Okay, then the other thing, and we'll talk about as we're talking about atomic weight of gases and that. So helium is a very light gas. Okay, so helium can actually get past certain airway obstructions. So for example, they've used it with asthmatics when they're having really severe bronchospasm. It's a lighter gas, it's more laminar, it's lighter weight, and it can actually help carry, it's a mixture of helium and oxygen, help carry the oxygen past that obstruction. Sometimes it's like in an asthmatic case, probably the place that I've seen it used more is like a tumor or something that someone might have in their airway or in the mediastinal area, like in their throat or their chest area, that's compressing or pushing onto their airway and making their airway more narrow and making it more difficult for them to breathe. Sometimes when we take out the breathing tube, you may have post-extubation stridor, where you have airway swelling in the upper airway. The idea is that helium helps make a more laminar flow, so it makes it easier for them to breathe, decreases that resistance. Okay. Right. Viscosity. Okay. So viscosity is how it kind of like hangs on to, you think of like maybe milk and honey, or water and honey. How honey is much more viscous, it's thicker. Okay. So the higher the viscosity of the fluid, the slower it's going to flow. So the viscosity of a fluid is directly proportional to the cohesive forces between its molecules. So the stronger these cohesive forces are, the greater is the fluid's viscosity. So you think about, the thick, cold honey, I can hardly get it out of the little squeeze bottle, and then we heat it. Okay, I put ours in the microwave sometimes for just a few seconds, and the heat actually helps increase, or rather decrease, the viscosity. It decreases the viscosity, it increases the flow. So when you look at viscosity and flow, if something has a higher viscosity, it's going to have a decreased flow. So that's inversely proportional. Okay, so increased viscosity, decreased flow. And so you think of sometimes, when people have a lot of secretions in their lungs and they can't cough stuff up, that kind of hangs on to the the airways, and it makes it more difficult for them to breathe. Also, it narrows their airways. So viscosities then of most fluids then decrease as you increase your temperature. So you think of like honey, as you increase the temperature, put it in the microwave a little bit, then you can finally squeeze it out of the bottle. Okay. So viscosity is another terminology, and that's probably the best way to explain that one. All right, we'll be digging a little bit deeper next time.